Hello friends, now we will see one university question on Mohr's moment area theorem for calculation of deflections. This is for JNTU in the year June 2016. The problem is defined here. It is a simply supported beam of span 8 meter loaded with uniformly distributed load of 20 kilonewton per meter. Obviously, we are not supposed to calculate the deflection by using the formulae. We have to calculate the deflection from first principles by using Mohr's moment area theorem. The values of E is given in Gn giganewton per meter square and moment of inertia is given in centimeter per 4. We have to convert this in kilonewton per meter square and meter per 4 respectively. E is converted into kilonewton per meter square. It is 2 into 10 power 8. Similarly, moment of inertia is converted into meter per 4 because the dimensions are in meters. All the units have to be consistent. Now, what is Mohr's moment area theorem? If there are 2 points on the deflected curve, let us say theta A and theta C, then the difference in the slope theta A minus theta C is equal to 1 by EI times area of the bending moment diagram between these 2 points. This is Mohr's theorem. Here we have been asked to calculate the slope at the mid span. That is one part of the problem. We have to calculate the slope at the mid span. That is the point C. Now we will apply Mohr's theorem for the 2 points A and C. Sorry, we have to calculate the slope at the ends. That is, we have to calculate the slope at A. Now we will apply the Mohr's theorem for the 2 points A and C. Theta A minus theta C is the difference in slope between the points theta A and theta C. As per Mohr's theorem, it is equal to 1 by EI times area of the bending moment diagram between the 2 points A and C. Now, what is the bending moment diagram area at any distance x from support A? What is the expression for bending moment? This is 20 kilonewton. Therefore, by which of symmetry this reaction is 80 kilonewton, and here the bending moment is 80 into x minus 20 into x square by 2. So there are 2 terms for the bending moment. 80 into x is one term, 20 into x square is one term. This is the ordinate. This is the bending moment ordinate at any distance. 80 into x minus 20 into x square by 2. Now, let us consider a small strip of width dx. So, this elemental area is ordinate into dx. There are 2 terms, 80x and this term. So, 80x into dx is one integration term, and this 20x square by 2 into dx is another integration term. This will give the total area contained between A and C. So 80x into dx, this is one part of the elemental area. This is another part of the elemental area. And this needs to be integrated between 0 to 4 because we are talking about the slope difference between the 2 points A and C. A is the reference point from which the section x is measured. Therefore, the limits are ranging from 0 to 4, A to C. This is the integration. Now, theta A minus theta C. Now, what about theta C? The deflected shape by virtue of the symmetry will be like a parabola, and if you draw the slope at C, it will be perfectly horizontal. That means theta C is equal to 0. By virtue of the symmetry, in the deflected curve, if you draw a tangent at point C, it will remain perfectly horizontal. Therefore, theta C is equal to 0. Then theta A minus theta C becomes theta A, and that is equal to 1 by EI, and then we are simplifying this integral. after simplification of integrals and after substitution of E and I values, we are getting the slope in radians. This you can multiply by pi by 180 by pi, so that you will get it in degrees. This is the slope at A. Similarly, theta B, the slope at the other end, that is also equal to theta A, that is also equal to 0.41 degrees. This is because of the symmetry. So by applying the Mohr's theorem between the 2 points theta A and theta C, we are able to get the value of theta A because theta C happens to be 0. This is one part. The other part is calculation of deflection at midspan C. Now, for midspan C, the deflection is given by the vertical intercept between the two tangents, and the vertical intercept should be measured at the point A. You consider point A and point C. Draw tangent at A as well as tangent at C. This is one tangent, this is another tangent. The vertical intercept measured from A, this is the vertical intercept. This happens to be equal to the deflection at the midspan, delta C. So instead of getting the deflection value delta C, we will try to get the vertical intercept at A. Mohr's theorem does not give the value of deflection directly. It gives the value of the vertical intercept between the tangents. At A, this is the tangent. At C, this is the tangent. And if you draw one vertical, this is the vertical intercept. So you are measuring the vertical intercept at A. That means you have to take the moment about the point A. Now, what is the elemental strip area? Mohr's theorem states that the vertical intercept between the two tangents is equal to moment of the area of the bending moment diagram between these 2 points. Now, this is the area of the bending moment diagram, and this is the elemental area, and this ordinate is measured from the distance x. This ordinate into dx is the elemental area, and this elemental area into x is the moment of the elemental area. And if this is integrated between 0 to 4, this gives the total moment of the area of the bending moment diagram between A and C. So 1 by EI times, and this bending moment ordinate has got two terms, 80x into dx. So 80x into dx. And what about the moment? Moment is you have to measure the distance. So x. So 80x into dx, and for the sake of moment, another x. What about the other term? 20x square by 2 into dx. This is the area into x, the moment. So this is 1 by EI times area of the moment of the bending moment diagram. After simplification of the integral and also after substitution of the E and I value, we are getting the deflection in meters, 0.0178 meters, and that is 17.8 millimeters. This is the value of delta C. Here you have to take the moment of the bending moment diagram about the A, because the vertical intercept between the tangents measured at A happens to be equal to delta C. We should not take moment about C, because if you take moment about C, it gives the vertical intercept measured at C. What is the vertical intercept measured at C? This is one tangent, this is another tangent. If you measure the vertical intercept at C, it is going below the deflected curve. It is in no way related to delta C. It is irrelevant. So we have to take moment about the point A. Here we know the area of the bending moment diagram by means of the parabolic property also. The parabolic bending moment diagram's area is equal to 2/3 of the enclosed rectangle, and its center of gravity is at a distance of 5/8 measured from A. So instead of integration, we can also directly put the area for the calculation of slope, and we can also directly put the area and the CG distance for calculation of the deflection. However, as a matter of general procedure, I have written down the values of the bending moment ordinate and I have considered the elemental area. Now, I am also requesting you to visit the site https://rgnsite.wordpress.com. Here two semicolons are missing. Sorry, the semicolon is there. // are missing. https://rgnsite.wordpress.com. This site contains about 500 university questions and answers on various structural engineering subjects such as RCC design, steel design, strength of materials, moment distribution, slope liquefaction method, matrix methods, etc. You can take these pages for free download. The download is free for all the block materials, including this page. It also contains lot of explanations in the form of one-word university questions and answers. So the detailed university questions and answers are also available for free download. Lot of explanations are given in the form of one-word questions and answers, including this page. Please visit https://rgnsite.wordpress.com. Thank you.